Hello, hi, good morning, everyone. My name is Benedict. I have my colleague Belen and Marie, and we have someone offline who's just recorded the presentation. Her name is Megan. So we're going to talk about hydrodynamism and its influence on the abundance of sea urchins.
I was just saying hello to Megan.
Sea urchins in the Mediterranean Sea. So what we're going to talk about here is that at first we're going to talk about, we will have an introduction, a little bit of literature review. And then we will present to you the hypothesis, the materials, and the methods, and discussions of the results, and as well as the conclusion. So now it's Megan.
Sea urchins play an important role as herbivores in the Mediterranean Sea ecosystem. Through their grazing, they can help regulate the size and composition of macroalgal assemblages. In this region, Paracentratus lividus, or the purple sea urchin, and Arabicea lixula, or the black sea urchin, are the two most common species. These two species help shape underwater landscapes in the shallow subtidal reefs of the Mediterranean Sea. At high densities, these urchins can change a macroalgal-dominated environment, like the picture shown on the left, to a coralline barren environment, represented by the picture on the right. Coralline barren environments are characterized by encrusting coralline algae. They host lower diversity and complexity. This structural change can be the result of P. lividus and A. lixula, and highlights how important these species are in the underwater landscaping of the Mediterranean Sea. The preferred habitat of these urchins is hard substrate such as rocks. They are also found in Posidonia, as it's similar to hard substrate, provides food and protection. P. lividus tends to prefer slightly deeper, more horizontal substrata, with A. lixula preferring shallower, more vertical substrate. One hypothesis for this slight difference in habitat selection is wave exposure. The literature has shown that hydrodynamics affects gonad production, choice of attachment site, feeding strategies, and growth rate of sea urchins. In terms of habitat selection, there have been conflicting results, with some studies saying increased wave exposure results in an increase in urchin abundance, and other studies suggesting the opposite, that it causes a decrease in urchin abundance. The current body of literature demonstrates that further studies are needed to determine how hydrodynamics affects urchin abundance. Our study aims to help answer this question.
For this, our hypothesis is, the first one is there is not significant difference between the position and shelter and exposed on the abundance of sea urchin. And the second is there are no significant difference among the substrates in regards to abundance of sea urchins. Talking about the methodology, first we collected data at the end of September of this year in Lerance Island, specifically in Saint Margaret and Saint Honora. We choose two positions because the direction of the waves in this site is northwest. So we choose exposed area that you can see is ESCA 2.4, ESCA 5.7, and ESCA 6.8 there. And we choose shelter position that is ESCA 3.8, ESCA 4.1, and ESCA 5.4. The sites is based on the current and the wind with the study period. So here you can see here we can see the coordinates of these sites. Sorry. About the data collection, first we choose time random stratified survey sample method. We have to observe, conduct 3-minute snorkeling, and we did three replicate time per seat. So we can see the percentage, one observe, see the percentage of coverage of different substrates, Posidonia, turf alga, rocks, and erect macroalga. Another observe, so the number of sea urchin in the first tree. In the second trial, the observed change. One observed did the percentage of coverage, and other person see the number of the sea urchin. And the third tree change again. So the first about the statistical tools and analysis of data. in our study, we did the two-way analysis of variance of ANOVA because analyze the interaction between the factors and the variable using the method nested design. Also, the two-way analysis of variance examines the effect of two factors and any relationship between the independent variables. Also, we need the two-key test because we want to know what specific covariable influence the abundance of CRG.
Okay, now I'll present to you the statistical model of this experiment. So here we have the dependent variables, which are the sea urchin density. And then we have another group of independent variable, which is the position, on which there is site within the position. So that becomes nested like Matryoshka dolls. All right, and then so within position, you've got exposed and sheltered. Inside position, you've got the sites, which are, we have this 6 sites, and each site would have 3 replicates. So this is one independent group. And then we have another group, which is the covariate, which represents the different substrates. So this particular model will measure the interaction between the dependent variables and the independent variables and the covariates, as well as for each group, as well as within the groups. All right? And also to identify which one actually affects the abundance of sea urchin, we use the two-key range test to do that.
All right, so now let's talk about the tables. So, yeah, you have
Here for me.
All right, so here this table, it shows frequency of the sea urchins on the exposed side. So here, as you can see, is only the exposed sides, and here are it's replicated 3 times. And here you can see the frequency. So at total in the exposed size, we observed 136.5 sea urchins. The next table show exactly the same, but with the sheltered size. So again, here are the size of that we took for the sheltered area, and here is the frequency of sea urchin we observed in these size. So 147. So now what we did here, well, with all the data showed in the tables before, we calculate the central tendency of this data. So here you can see in the box plot and also in this table that the means are really, really close from each other, so really similar. However, there are some outliers in these results. So what our outliers do? Well, they pull the mean up. So we had to find a solution to remove these outliers. So what we did, we removed the outliers, and when we removed the outliers, well, there we realized a huge difference between the means and the median. So here you can see that was with outliers, and that is without outliers. However, Bene later in the presentation will explain you why we decide to keep one of the outliers in the sheltered. So we keep this one, and Bene will later on explain why. So here you can see a difference in mean. So for the exposed is 14.83, and for the shelter is 5.25. So here, when we saw that, well, we expected, because it seems to be that the exposed area, the abundance of sea urchin is more in the exposed area than in the sheltered area. So that's what it seems to be. Yeah? Okay, so that was for the exposed and the sheltered area. Now we do the same, but for the different substrates. So here you can see the column or the substrate, the row again are these different sizes. And here is the percentage coverage of the sea urchin. So here, for example, you can see in rocks, there is really not a lot of rocks observed. Yeah? So that's exactly the same for shelter. Again, for example, if you look at rocks, you can see that there are only few rocky substrate observed. And actually, so what we did, we took 2 tables, the 4 table I just present, and here we make a resume. So what does the pie chart show you? Well, in colors, the different colors are the substrate coverage. So for example, you can see here in blue, in this area, they were observed way more erected macroalgae than rocks, for example, and I think even no rocks at all. So the color differentiates the substrates, and then the size of the
pie chart.
Sorry for my accent. Of the pie charts represent the abundance of sea urchin. So, for example, here we observe way more sea urchin than on these sites. So that's what this figure explains.
All right. So after doing the calculation in TUI and ANOVA, of course we did some checking for assumptions, and after checking the assumptions using observed data, all the assumptions passed. However, after the calculation, it's actually ideal to check the assumptions using residuals instead to verify whether the use of ANOVA or whether all the assumptions have been met or not. So during the checking of the residuals after the first ANOVA test, we discovered that, okay, we passed the test for linearity, we passed the test for normality, and our data is the test for homoscedasticity is also passed. However, we have a problem with the outlier, as mentioned earlier to you. Now, this particular chart here represents the structure of the data. Here you can see that you have a very low residual but very high leverage. So this particular leverage here is pulling the slope of the regression line towards the outliers. However, we all know that when you talk about outliers, they could be, there's really something wrong with the data, or it could actually be a data. All right, so we tested the outliers, and we noticed that there were, after doing Rossner's test, these two data points here were an actual outlier. However, this particular data point here is not an outlier. It can also be represented here in this diagnostic plot. The rule for this diagnostic plot is whatever is outside of the Cook's line is said to be highly influential, very high in leverage, meaning to say it's actually pulling the slope towards that data point. If it lies between 0.5 and 1 of the Cook's distance, it can be considered, but still further testing needs to be done, which we did. And true enough, after adjusting the data, we finally passed the test for outliers. So that data point number 10 over here is still retained, hence the box plot that Marie showed you previously. So we did another set of ANOVA tests. And what we discovered is that there's actually no significant difference on the position, meaning to say sheltered and exposed, they don't have any significant difference, as well as with regards to site within position, there are no significant differences. And as well as, sorry, it's cut, as well as the position with a site within position and substrate. So these three groups here are not significant at all. So here we can deduce that hydrodynamics has no significant effect on the abundance of sea urchin. However, we also tried to figure out what actually influences the abundance, because we know that there's still another factor that could have influenced it. If it's not hydrodynamics, what could it have been? So we did Tukey's range test, on which we look at the different substrates. What influenced the abundance or settlement of sea urchins on this site, on our site? And after Tukey tests, we had a significant different result for erected macroalgae as well as Posidonia. Right, so this gives a very high, very low p-value. And this is also supported by the f-value that we have. So this is the statistical summary of the whole test that we did. So here, as you can see, there's actually no significant difference between groups with values higher than the p-value. All right. However, within the substrate group, there's a significant difference among all of them within the group. Doing some Tukey tests, now we found out that for this covariance that must have affected the abundance of sea urchin, it's the macroalgae and the Posidonia that gave the much higher influence on the abundance of sea urchins.
All right, so to conclude, so what did we do?
sorry.
It's okay. So first of
Oh,
all, we
yeah.
went to Les Rance Islands. Okay. What we did, we observed. Yeah, we observed. Then with the data we had, we came up with an idea like, what can we take out of it? Well, we find the research question on the urchins, well, where we wanted to know, so if the abundance of sea urchin was because of hydrodynamics or because of substrates. So that's why we come up with these two hypotheses. Okay, and yeah, you can. Okay, and now here, thanks to the two-way ANOVA, we figured out that there is no significant difference in our results between the two positions, sheltered and exposed. So we accepted the null hypothesis, and then for this hypothesis, bless you, there are significant difference among the substrates, among the different substrates regarding the abundance of sea urchin. So we reject the null hypothesis. However, we use the Tukey test to see which one was the most influential, and we discovered that it was the erected macroalga, and the Posidonia. So that's our conclusion. So we really went from observing to the
44 seconds. Okay.
These are the reference.
These are our reference. Yeah. And thank you for your attention.
Thank you.
And if you have any questions,
I'm sure.
When have you done your sampling? When have you done your sampling?